Good morning, dear children. Our next topic is optical instruments. And the optical instruments which we are going to study here is about microscope and a telescope. You have studied about an optical instrument which is present in us, that is human eye. Inside there is a convex lens. And you have studied about the working of that also. So in this topic we will study two optical instruments, that is a microscope and a telescope. First let's come to a microscope. An ordinary microscope can be of two types. One is a simple microscope, which means it is a simple convex lens. Just a convex lens acts as a microscope. Microscope means something which can make the object bigger, appear as bigger. So a convex lens, if you hold in front of an object, you can see a bigger image of that. That means it is acting as a magnifier, a simple magnifier. That is a simple microscope. Another one microscope is what you are using in the biology lab. That is called a compound microscope, which consists of two convex lenses. So let us first consider the case of a simple convex lens, that is called as a simple microscope, in which you keep the object near the convex lens and you see the bigger image. So when coming to the image formation, all the images formed in front of your eyes, if it is at a distance 25 centimeter or nearby that, your eyes can comfortably see that. If it is very close to your eyes, if the image formed is very close to your eyes, then you will not be able to see that clearly. So for an image to be seen well, the image should be at least at 25 centimeter, which is known as the least distance of distinct vision, represented as capital D. Now what happens when you keep the object near the lens and the image is formed nearly at 25 centimeter from you? So let's consider a situation in which you have a convex lens here. This is a convex lens and it has an optical center. You place an object here. This is the object here, AB, which is making an angle beta with the principal axis as shown in figure. So this AB, this object, makes an angle beta here with the optical center with the lens. So this is our object AB. Now when you observe this object, its image will be formed almost at 25 centimeter, so that you can see the image very clearly. So let IM stands as the image formed here. This is the object here, this is the image formed here. This can be obtained by drawing the ray diagram. So this is AB. Two rays we can consider. From the top we can consider two rays. One is passing through the optical center without any deviation. Other one going parallel to the principal axis after refraction passing through the principal focus. So this is the procedure of getting the image here. Now extend these two rays, because these two are not joining anywhere. So in that case we get a virtual image and not a real image. So in all such situations we extend the rays and you get a point here. This is the image formed, that is IM. Suppose if this is I and this is M, IM stands for the image formed here. So object is AB, image formed is IM. The magnified image is IM. And that magnified image also will make the same angle beta with the principal axis. Now in this case, as the image is virtual, we cannot measure what is the height of this image. We can measure what is the height of the object, but we cannot measure the height of the image. So in that situation, what we can do is, when the image formed is virtual and we cannot measure the height of this image manually, what we can do is we think about a particular magnification which is known as angular magnification. So if you want to find how many times this image is bigger than the object, there is no other way. You cannot measure it using a scale. You cannot measure the image formed here. So what we can do is we can take the angular magnification, which is a particular way of defining the magnification in a lens. So here what you need to do is you need to find the ratio of angle subtended or angle made by the image to the eye at D. When the image is formed at D, what is the angle made by the image compared to the object when it is at D, divided with the angle made by the actual object at D. So what you need to do is ratio of angles we are taking in order to define the magnification. We know magnification is height of image by height of object. This is not practical here, as the image is virtually formed in front of your eyes. So what we do is we take the angular magnification, which is the ratio of angle made by the image when it is at D with the eye, to ratio of it is divided by the angle made by object at D. So here in this picture you can see this is the actual object and this is the image. IM is the image. So angle made by image at D means this image makes an angle beta with the lens principal axis. So angle made by image is beta, angle is beta. Angle made by object at D. You need to think object at D. That is what here we have shown. At the same place at D, we have marked the object, AB sized object we mark here. That is IM dash. This is actually the object placed at D. This is the way of defining the magnification. So object, this AB, if you place at a D, it makes an angle alpha with the principal axis. This beta by alpha is actually our magnification. Why we go for this definition is, if angle made by image to angle made by object, if we take the same angle, it makes AB makes the same angle as that of IM, but the definition is angle made by image IM at here, that is beta, divided by angle made by object at D, that is IM dash. This is the object at D. Their ratio is magnification. So in this case what we do is we can take as the angles will be smaller, or in all cases angles will be smaller here, and that angles can be approximately taken as tan theta, because for small angles tan theta is approximately equal to theta. So let's see the parameters used here. AB, the object placed between optical center and the focus. IM is the image. Alpha is the angle made by object at D, when object is at D with the eye. Beta is angle made by image at D with the eye. Angular magnification is known as angular magnification, that is beta by alpha. And we told for small angles alpha and beta can be approximately taken as a tan alpha and tan beta. So from this, if you take tan alpha, you get tan alpha is opposite side IM dash divided by this length, that is from here to here, adjacent side D. IM dash by D is alpha, tan alpha. If you take beta, opposite side is IM divided by the same D. So from both triangles we got tan alpha and tan beta. We divide that, we get IO by AO, IO divided by AO, which is IO is D and AO is U. If we take beta and alpha, so look at the triangle once again. Alpha, when you take this angle alpha, this is IM dash divided by this length, that is a D, that is tan alpha is IM dash by D. And beta, if you consider, you can consider this big triangle, or even this triangle also we can consider beta. For beta we can consider this angle also, ABO, that is also making the same angle. So tan beta, if I take, I get AB by AO. AO is nothing but the object distance, so this is also possible. I'll write here. So here tan, look at this figure, tan of beta is AB by AO, and tan of alpha is IM dash divided by IO. IM dash is nothing but AB itself, because their length is equal. AB is itself divided by IO. IO is D, and this AB is here divided by AO. AO is the object distance. This is the object, so AO is object distance U. So tan beta is, we told for small angles tan beta is approximately beta, and for tan alpha it is approximately alpha. So if you divide these two, what you get is D by U. So that's a magnification produced by simple microscope as a D divided by U. D is 25 centimeter, our least distance of distinct vision. So the same equation can be framed in terms of focal length also. For that, what you need to do is this D by U, let us check using lens formula. 1 by F is 1 by V minus 1 by U. Multiply this with the D, then it becomes D by F, my D by D by V minus D by U. And we know that V is the image distance. Image is formed at D itself on the left side, so V and D are equal. V and minus D are equal, so this V I can substitute as minus D, and U is the object distance, that is also on the left side, so let U is negative. So what happens is D by F is equal to, this is minus 1 minus D by minus U. This U is again negative, so this should be substituted as a negative, then it becomes plus D by U. Then you get a D by F is equal to minus 1 plus a D by U. Our magnification was, just now we got magnification as a D by U. So in that case our D by U is taken here, it is kept here, this term alone taken to the left side. So 1 plus D by Fe, sorry D by F, that is our magnification. So magnification of a simple microscope when the final image is formed at D at 25 centimeter in front of our eyes, that is 1 plus D by F or D by U, both are same, D by U or 1 plus D by F. This is in terms of focal length of the lens, this is in terms of the object distance. We know that a human eye is comfortable in viewing the object when it is at 25 centimeter, you can clearly see that. But if you see the object at 25 centimeter close to your eyes for long time, definitely your eyes will be in strain. So the most relaxed position of your eyes is when you look at an object which is very far, which is at infinity. So when the image is formed at infinity, your eyes are very relaxed. So that is a particular case that is also possible with the help of a convex lens, because if you keep the object at a principal focus of the convex lens, you get the image at infinity. So in that case you can view the image very relaxed way for your eyes. So that is also a particular situation for a convex lens, a simple microscope. simple microscope or convex lens can produce image at two different places for our importance. One is at 25 centimeter, if so magnification is 1 plus d by f. Another one situation, image formed can be even at infinity, so that your eyes are very relaxed. So for image to be at infinity, object should be placed at a principal focus. So again, let's consider a convex lens here, and at its principal focus at f itself you keep an object AB, and that object makes an angle beta with this principal axis, same as like the previous one. So as the object is here, if you plot the ray diagram, one through the optical center, it goes like this, another one passing through the principal focus, these two lines will be very parallel. Situation, when the object is at f, the two lines are parallel, image is formed at infinity. So this is the focal length, image will be formed at infinity. So in that case we cannot locate the image. What we will do is we define the magnification in a different way, in a slightly different way. Here magnification is angle made by image to the eye at infinity divided by angle made by object to the eye at d. So at d you keep the object at d, what angle it makes here, that is alpha, this angle is alpha, and the angle made by image at infinity. When the image is at infinity, somewhat here, approximately very far in the same direction, the angle is beta. So here also beta by alpha will be the magnification. So what we do is we take tan beta by tan alpha. So tan beta here is, in the figure, tan beta is AB by OF. AB tan beta opposite side by OF. That is the angle beta, and alpha is A dash B dash image divided by this distance is capital D. So this A dash B dash is equal to AB, so AB by D we get. So the two things if you divide, you get AB by OF divided by A dash B dash by A dash O. Then that A dash B dash and AB cancel because they are equal, so you get A dash O by OF, which is A dash O is D minus D as it is on the left side, and OF is focal length on the left side. So magnification is D by F. So two situations, convex lens, when it is forming image at infinity, magnification is a D by F. When it is at the near point, least distance, it is 1 plus a D by F. So that's about a simple convex lens, a simple microscope. So once again rewinding, a simple convex lens means it's a simple microscope. It can produce image of magnified size. So two possibility, one is image formed at D, in that case magnification is 1 plus D by F, and other one image formed at infinity, that case D by F. So this image formed at infinity is also known as a normal adjustment. Normal adjustment means the image is formed at infinity, in that case you get magnification as a D by F.